Today we are going to talk about the number of ways an event can happen. So for our first example, Mr. Hill gets up early and chooses his clothes in the dark. He has 2 pairs of pants, 3 shirts, and 2 ties. And he's just going to throw together an outfit out of those 3 items. Find the number of ways that the outfit could be chosen. So Mr. Hill has a pair of blue pants. With those blue pants, he could put on a white shirt, or a tan shirt, or a yellow shirt. But with his blue pants and white shirt, he could put on a red or purple tie. And with the blue pants and tan shirt, he could put on a red or purple tie, and blue and yellow could go with a red or purple tie. Mr. Hill also has a pair of gray pants with which he could wear a white, tan, or yellow shirt, and with each combination there, he could wear a red or purple tie. So that's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different outfits that Mr. Hill could put together with that combination of clothing. Each different outfit is an outcome, and each one is called, in probability, it's called an event. An independent event is an outcome that is not affected by other picks. So when you're choosing your clothing in the dark, and you're just grabbing a pair of pants and a shirt and a tie, then in that case, what color pants you wear makes no difference on the color of shirt you wear. Now in reality, probably once you pick one item, you narrow down your choices for the next, and those are called dependent events, an outcome that is affected by other picks. Okay? So this is independent because the choice of pants did not affect the choice of shirt or the choice of tie. No one choice affected any other choice. So in this case, it is independent. Okay? Now, if we have 10 pairs of pants and 30 shirts and 27 ties, this tree diagram here is going to get awfully big. But we can use the basic counting principle for any independent events. So if one event happens in M ways and another in N ways, then the total possible outcomes is M times N. Right? So in this example over here, there were 2 pairs of pants and 3 shirts and 2 ties, and 2 times 3 is 6, times 2 is 12 different ways that the outfit could have been chosen. Okay, so instead of drawing a tree diagram every time, we can multiply the number of choices from each category. A group of 3 representative patients are needed for a study. Dr. Smith has 11 patients, Dr. Pepper has 7, and Dr. Phil has 24. If we are going to choose one patient from each doctor, are the selections independent or are they dependent? The answer is they are independent. And it's because the first pick does not affect the second. If I'm picking one from Dr. Smith, that has no effect on the patient I choose from Dr. Pepper or from Dr. Phil. So the first pick does not affect the second. It also doesn't affect the third. The first doesn't affect the third. The second doesn't affect the third. So in how many ways can these groups be selected? So the first doctor had 11 patients. The second doctor had 7. And the third doctor had 24. 11 times 7 times 24 is 1,848 different ways that we could choose one patient from each doctor. If all 3 patients come from Dr. Phil, is it independent or dependent? In that case, it is dependent. Okay? When I make my first choice, that affects the odds for the next choice. And that second choice affects the odds for the third choice, because Dr. Phil has 24 patients, and when I'm picking the first one, I'm picking 1 out of 24. When I'm picking the second one, I'm picking 1 out of 23. Then I'm picking 1 out of 22. So because the odds change each time, that is called dependent events. Okay? In dependent events, a permutation is a set of objects arranged where order matters. Okay? Think of things like a lineup. Okay? If 2 people trade places, it's a different lineup. Okay? So a lineup is one where order matters. Maybe specific roles. If 3 people have specific roles and then they change roles, that changes the permutation. So a permutation is NPR, where N is the total number of objects, R is the number of picks to choose that we're using, N factorial, which means, say, 5 factorial would be 5 times 4 times 3 times 2 times 1, over N minus R factorial. So using the letters A, B, C, does order matter if we're finding the possible arrangements? Yes. Arrangements is another word that might tell you that order matters. Okay, so in a tree diagram, we could have A first, then B, then C. Or we could have A first, then C, then B. We could have B first, then AC, or then CA. We could have C first, then AB, or BA. 1, 2, 3, 4, 5, 6 different options. So there are 6 ways to arrange the letters A, B, and C. Or if we do this as a permutation. So a permutation with N and R, 3 total objects using all 3 of them, is N factorial, the total number factorial. So that's 3 times 2 times 1. I'll try to squeeze in there. Let me just back it up and write that that is 3 factorial over N minus R factorial. 3 minus 3 factorial. So that's 3 times 2 times 1 over, and this is really 0 factorial, and we can't really count down to 1 from 0, but 0 factorial is defined to equal 1. So we've got 3 times 2 times 1 over 1, and that equals 6 different ways that the letters can be arranged. If order does not matter, how many combinations? So combinations means that we are not, we don't care about order, it's not an arrangement, it's not a lineup. How many different combinations are possible using all 3 letters from A, B, and C? There's only one combination, because ABC is the same combination as BAC, and so on. No matter how I arrange them, it's still the same combination. So there's only one combination using all 3 of these letters, but there are 6 permutations, 6 ways that I can arrange them differently. From the full alphabet, how many ways could we arrange 3 different letters? Okay? So arrange tells me that order matters. Okay, so I'm going to make a note over here. Order matters. So that means it is a permutation. Okay, it is a permutation with 26 to choose from, but using only 3 different letters. Okay, so as a permutation, 26 factorial, that's n factorial, over n minus r factorial, 26 minus 3. 26 options, but only using 3 of them, factorial. Okay, so that's 26 times 25 times 24 times 23 times 22, all the way down to times 1. Over 26 minus 3 is 23, so that's 23 times 22, all the way down to times 1. The 23 cancels, the 22 cancels, the 1 cancels, everything in between. So we're left with 26 times 25 times 24. And that is 15,600 ways to arrange 3 letters out of the entire alphabet of 26 letters. Okay? Another way to think about that would be like this. If I've got 3 spots to choose from, I'm going to put a letter in each of those 3 spots. In the first spot, I've got 26 to choose from. In the second spot, I've already used 1. Now I've only got 25 letters to choose from. Now I've used 2 letters, so I've only got 24 letters to choose from. That ends up exactly the same as what we have there. In a combination, it's similar to a permutation, but order does not matter. Okay, so a combination is n factorial over n minus r factorial times r factorial. Okay, so 3 of Dr. Phil's patients are selected to sit on a committee. If they all have exactly the same role, does order matter? No. It only matters if they each have their own specified role. So how many different groups of 3 patients can be formed? Okay, so we're doing a combination. We have 24 patients to choose from. We're going to use 3 of them. So that would be 24 factorial over 24 minus 3 factorial times 3 factorial. So it's 24 times 23 times 22 times 21 times 20 times 19, all the way down to times 1. Over 24 minus 3 is 21, so 21 times 20 times 19, all the way down to times 1, but also times 3 factorial, so times 3 times 2 times 1. So what cancels is 21 and 20 and 19 and 18, 17, 16 down to 1. So we're left with 24 times 23 times 22, all over 3 times 2 times 1, which is 6. So the product of all 3 of these divided by 6, and that comes out to be 2,024 different ways to choose 3 of Dr. Phil's 24 patients. But what if everyone on the committee has a different role? Okay? If there's different roles, now order matters. So we're using a permutation. 24 options, using only 3. Okay? Now I'm going to do the more simple version here, because we've seen up here that a whole lot of stuff just cancels, and we only have 3 roles that are being filled. So there are 3 roles to fill. There are 24 total patients, so for the first spot, I've got 24 to choose from. For the second spot, now I only have 23 left to choose from. For the third spot, now I only have 22 left to choose from. 24 times 23 times 22. Notice it's very similar to what we had here for the number of combinations, except now we don't have to divide by 6, so it's going to be a bigger number. 12,144 different ways to arrange. Okay? There's usually going to be more ways to arrange numbers than there are just to choose them.